So I have the great pleasure of hosting a brilliant computer scientist, Professor Scott Aaronson. So, Professor Aaronson, thank you so much for your time and for doing this podcast.
Sure, it's a pleasure.
Okay, so I would like to start our discussion with questions on quantum computation. What do you see as the biggest practical and theoretical challenges we need to solve before we see widespread useful quantum computers?
Well, I think the biggest challenges are, as they were 30 years ago, although, of course, there's been a lot of progress since then. The biggest practical challenge is to engineer devices that can manipulate qubits, to a high enough degree of fidelity. Uh, Ideally high enough that quantum error correcting codes can then get you the rest of the way to doing a full fault tolerant quantum computation. The biggest I mean that's the biggest practical challenge for the quantum
Mhm,
computing systems builders. And just within the last year we've finally seen the first error corrected qubits that are starting to really perform better than the underlying physical qubits are performing,
mhm,
and they could look like they could be building blocks of a future scalable, fault tolerant system. Okay, but there's a lot of work still to do to
mhm,
make it really practical. And then on the theoretical end, the biggest challenge is still to figure out what are quantum computers good for. So
mhm,
there are a few famous classes of problems that have emerged as benefiting from a potentially exponential quantum speed up. The
mhm,
two biggest ones are simulating quantum physics and chemistry themselves, which could be useful for material science, designing new drugs, designing better cells, or high temperature
mhm,
superconductors. And then secondly, breaking the public key cryptography that currently
mhm.
protects the internet, which is not necessarily good for humanity, but good for
Yeah.
whatever intelligence agency gets that capability first. If we don't switch in time to quantum resistant crypto systems. So and of course, people have continued looking for more applications of quantum computers
Mhm.
beyond those two families. Okay, so we know of a very important quantum algorithm called Grover's algorithm that
Yeah.
is much more broadly applicable, beyond sort of those two domains. But its speed up is more modest. It is not
Mhm.
exponential. It is merely, quadratic, by a square root amount. Okay, but eventually we do expect that we could see Grover speed ups for a large fraction of all the sort of workhorse problems of computer science.
Mhm.
But then, if you want exponential speed ups for other problems, I mean, I would say that remains a very active theoretical research topic to this day.
Mhm.
People are looking for, are there combinatorial optimization problems where quantum computers can at least give you a better approximation than classical computers can in a
Mhm.
reasonable amount of time? Are there machine learning tasks that could benefit from a quantum speed up? Some people, for fundraising purposes, would like to confidently claim that we can do all of that. But
Mhm.
I think the truthful answer is that remains an active research topic now, and remains
Right.
maybe the biggest theoretical problem.
Right. So, do you think could the achievement of quantum supremacy force us to maybe rethink the nature of intelligence or creativity?
Well, I would say that to whatever extent it causes us to rethink these sort of fundamental questions, then we can already do it now, right?
Mhm.
Or we could already do it as soon as the idea of a quantum computer was proposed. We don't have to wait for the actual device in order to do that. I mean, I think philosophically, the biggest thing that quantum computing did is that it showed us that sort of what is efficiently computable and what isn't, is not something that we can decide a priori, just sitting in
Mhm.
our armchairs, right? It is ultimately an empirical question.
I
And
see.
concretely, quantum computers pose a severe challenge to what was called the extended church Turing thesis, which is the
Mm-hmm.
idea that everything in nature should be efficiently simulatable by a Turing machine, by a classical
Mm-hmm.
computer, like the one that we're using now.
Right.
So uh, uh, um, I think that's not directly about the nature of mind or creativity or anything
Mm-hmm.
like that. I do think it's a big deal, right? But as for the nature of mind and creativity, all the evidence that we have so far is that the brain,
Mm-hmm.
whatever is going on in the brain, in the human brain at the subatomic level, to
Mm-hmm.
whatever chaotic events influence whether a neuron fires or doesn't fire or anything like that. Once a
Mm-hmm.
neuron is firing or not firing, that seems like an entirely classical event, right?
I
That
see.
seems like something that and so to the extent that we can model the brain, as a neural network, as neurons that might have some stochastic component, but in the end are
Mm-hmm.
either firing or not firing, then to that extent it seems like a classical computation, that can be understood on the basis of classical computer science. And
Mm-hmm.
indeed the incredible successes of large language models, and other
Mm-hmm.
generative AI over the last 5 years, has underscored, has provided a dramatic, empirical demonstration of just how much intelligence you can get, purely from classical computation. So I think it remains an open question whether quantum mechanics is relevant to our brains in any way. But if it were, then it
Mm-hmm.
would have to be sort of below the level of individual neurons, as far as
I
I
see.
can tell. Yeah.
Okay, and what do you personally think about the nature of reality?
What I would say is that quantum mechanics is arguably, the deepest empirical fact that humans have ever
Mm-hmm.
discovered, about the nature of reality, right? Because
Mm-hmm.
it's not a change to some, detail of physics, like, like the exact way that particles move. It's not even, merely a change to space and time, right? Which is what
Right.
relativity does. Quantum mechanics changes our whole notion of what is the state of a physical system at all, right? And
Mm-hmm.
how do we calculate the probability that something happens? So, it changes things that you might have thought were just logically a priori, where,
Right.
that seem more like math than like physics. Uh,
Mm-hmm.
in particular, it tells us that, any isolated physical system that can be in, different states can also, that are distinguishable from each other, can also be
Mm-hmm.
in what we call a superposition of those states. It can be in a complex linear combination of them. Okay,
Mm-hmm.
and the quantum mechanics has been clear about that for a century now. Right, that's the
Yeah.
entire basis of modern physics, uh,
Mm-hmm.
and yet there's still not, a universal agreement about what it means. Right.
I
Does
see.
it mean that we have to give up on just an objective description of reality, that we just have to content ourselves with calculating the probabilities, that we
Mm-hmm.
will see various measurement results? That was the sort of original Copenhagen view.
Right.
Or should we take this math literally? And if it is talking about these superpositions, should we take
Mm-hmm.
them as themselves as the fundamental reality? That is what the many
Mm-hmm.
worlders would do, right? And
Yeah.
if you pursue that line of thinking to its conclusion, then you would say that even a measurement is just an artifact of our limited vantage point. Really,
Mm-hmm.
what's happening is just that we get entangled with the systems that we
Right.
measure, and the world itself splits into multiple branches. In one of them,
Right.
we experience one outcome, and another we experience another. And if so, then there were all sorts of doppelgangers of ourselves, whose
Mm-hmm.
life histories have turned out differently. Or should
I
we
see.
say, like the Bohemians, that yes, there are all these branches, but sort of, only one of them is actually experienced. And the rest of
Mm-hmm.
them are ghost towns, right? And now, you get into these questions that go back not 100 years, but but thousands of years, right? Until,
Right.
what is the nature of our subjective experience? How does that
Hmm.
relate to the physical world, right? And quantum mechanics has not answered those questions, and yet it has
Hmm.
somehow changed the discussion of them, right? It has
I
added
see.
a new twist to these thousands, to these millennia old mysteries, which are maybe, the central mysteries of all of existence, you could say.
Hmm.
And now quantum computing, at one level, quantum computing is merely, quote unquote, an application of the laws of quantum mechanics as we've
Hmm.
known them since 1926, right? It's merely a new technological application of these known laws. But at another level, quantum computing has provided, I would argue, maybe, the clearest language with which to
Hmm.
understand quantum mechanics itself. I mean, it has
I see.
changed how many of us teach quantum mechanics to
Yeah.
undergraduates, and
Hmm.
I think, it just lessens the prerequisites for, understanding the basics of this, to, just being able to manipulate matrices and vectors, right?
Hmm.
And furthermore, building a large scale quantum computer will arguably be the most dramatic test of quantum
Yeah.
mechanics itself that we're ever going to see, right? And, to this
Right.
day, there were some skeptics who say that
Hmm.
we will never succeed. That, either because, we totally haven't understood quantum mechanics, or because quantum
Hmm.
mechanics is wrong, right? And what I say to those people is, well, I hope you're right, because if you're right, that will
Hmm.
be a revolution in physics, right?
Exactly.
That a quantum computer will work like the theory says is the more conservative possibility. It's the, the
Hmm.
more boring possibility. But either way, of course, we would like to find out the truth. And
Yeah.
so getting this dramatic confirmation of quantum mechanics could, it could sort of make these sort of, philosophical and metaphysical questions vivid
Hmm.
for people, in a way that nothing else has, arguably. And certainly, if you had solved both the problem of building a fault tolerant quantum computer and the
Hmm.
problem with AGI, right? And so you had, AGIs that everyone agreed were conscious. Maybe that's GPT-8 or whatever. Well, then, an
Hmm.
old argument that David Deutsch made, more than 40 years ago, was that
Hmm.
at that point, it seems almost like we could experimentally test the many worlds theory, right? Because we could
Hmm.
then load our AGI onto a quantum computer, put it
Right.
into a superposition of two different mental states, having two
Hmm.
different thoughts, and then do a measurement where we measured the interference and where we demonstrated that it really was in a
Hmm.
superposition of those two states. And at that point, to whatever extent we agreed that the AI was conscious, we would have to agree that yes, consciousness can exist in superpositions of states, just like the many
Hmm.
worlders had said. Okay, the only way out would be to deny that the AI was conscious, or maybe to deny that any AI could be conscious. Okay, but
Hmm.
at that point, the questions of what does quantum mechanics mean, and the question of what gives rise to consciousness, can an
Hmm.
AI be conscious, from that point forward, those questions are just completely entangled with each other. So,
Right.
that's the way in which I think that this does touch on, some of the biggest
Hmm.
mysteries that humans have ever wondered about.
Yeah. So, and now, when you mentioned the consciousness,
Mm.
what do you think about Roger Penrose theory that consciousness could be linked with quantum effects?
Well, I mean, I admire Penrose for his daring in sort of
Hmm.
asking these questions at all, right? When he wrote his book, The Emperor's New Mind in 1989, right? I mean, that had a
Hmm.
huge effect on me as a teenager, right? Because,
Hmm.
even, before Shor's algorithm, before quantum computing was even a subject, he was explicitly talking about it, right? He was
Yeah.
and he was raising all sorts of other questions. What is the physical basis of cognition? If you can you model neurons as as sort of classical computational elements? Is there other physics that's relevant? And he was bringing in computability theory, complexity theory, asking in what sense is the Mandelbrot set uncomputable, for example.
Mm-hmm.
So and even questions that have even been influential scientifically, right? Um,
Mm-hmm.
but then I really loved what Penrose was doing insofar as he's raising the questions. But then I become much less a fan insofar as he claims to have specific answers to those questions.
Mm-hmm.
Right.
I see.
And so at some point, Penrose got in touch with Stuart Hameroff, who is,
Mm-hmm.
an anesthesiologist, who said, I know the key, right? The key is it's these microtubules, which are these
Mm-hmm.
structural elements in many cells, not just neurons, right? But it must be the microtubules and neurons must be sensitive to new physics, right? And then
Mm-hmm.
Penrose said, from an argument involving Gödel's incompleteness theorem, we can just deduce, sitting in our armchairs, that the brain must be uncomputable, right? How can
Yeah.
we deduce such a thing? Well, it's because any computer program, right, will be, if it's just working out the consequences of some set of axioms, that we'll never be able to
Mm-hmm.
see that those axioms are consistent. But I can just see that the axioms of piano arithmetic, for example, are consistent.
Mm-hmm. Right.
Visualize the positive integers in my mind or whatever, and I don't see how any computer could ever do that, right?
Mm-hmm.
This argument from the get-go, I regard as invalid. Okay, I regard as a
Yeah.
fallacious argument, because and the answer to it fundamentally was given by Alan Turing, already
Mm-hmm.
75 years ago. He said it's true that you can't be there are, Gödel's theorem and related results tell us that no formal system can be both omniscient and infallible. Okay, but humans
Mm-hmm.
are not infallible either, right?
Yeah.
If we grant ourselves the liberty to make mistakes, to say, we don't know, well, then, we should grant computers that same liberty. And in that case, I mean, look, GPT can already very intelligently discuss Gödel's theorem and all the issues
Mm-hmm.
around it, and even Penrose's arguments about Gödel's theorem, is it infallible? Of course, it's not infallible. Okay, but
Mm-hmm.
it can now do math, at the level, Terry Tao has said, of at least a mediocre graduate student,
Mm-hmm.
in mathematics, right? And that's 3 years ago. Let's say it was in elementary school, right? Now it's in
Right.
graduate school, right? So I mean,
Yeah.
that's the pace of improvement that we've seen, and so
Mm-hmm.
I do not confidently. I don't see how anyone could confidently predict that if 5 or 10 years from now, we won't have AIs that can write research papers for us, that can
Exactly.
do original mathematical research. And so
Mm-hmm.
I think, that whole argument, is a fallacy, but then it leads Penrose to say that then the brain must be doing something uncomputable. That
Mm-hmm.
uncomputable thing, he knows enough to realize that can't be just the existing laws of physics, right? It has to
Right.
be something else. And then he says, well, where could the something else be? Well, the one thing we don't really understand is quantum gravity. So it must be there. It
Mm-hmm.
must be in quantum gravity.
Yeah.
How could quantum gravity possibly be affecting the brain? Well, then he's, because of what Hameroff says, he says it must be via the microtubules, right?
Mm-hmm.
And at
I
this
see.
point, you get this sort of theory, like every step of which I object to, right? I object to the original motivation from Gödel's theorem. I object to
Mm-hmm.
the idea of Turing uncomputability and quantum gravity, and I object
Mm-hmm.
to microtubules as something that we can know in our present
Yeah.
state of knowledge are sensitive to these kinds of effects. So I do think that there's a big mystery here, but I think that this that specific sequence of answers, I mean,
Mm-hmm.
I don't see that it's held up well over the last 30 years. I don't see that it's been, scientifically all that fruitful.
Mm-hmm. And what would you say is the role of a computation in understanding the universe? Do you think that the universe itself is fundamentally computational?
Well, it is. in a way, it's almost boring to say that the universe is a
Uh-huh.
computer, right? You could say, the notion of the modern notion of what a computer could be is so broad that you almost
Mm-hmm.
have to ask, like, what would the universe have to do in order to not be a computer, right?
Right.
In order to not be computational. I mean, you know, so ideas like Penrose's at least let us get more concrete about that question, right? Because
Mm-hmm.
Penrose believes that the laws of physics allow Turing uncomputable problems to be
Yeah.
solved. Now, I don't. As I said, I don't think that he has any good evidence for that. Okay, but even
Mm-hmm.
even supposing that it were true, supposing that
Mm-hmm.
we found some magic box on the beach that could solve the
Yeah.
halting problem, or solve some uncomputable problem, we could just say, well, that's just telling us that the universe is still a computer, but it's a more powerful kind of computer
I
than
see.
the Turing kind, right? Who is to, and so if your notion of what a computer is general enough, then just saying that the
Mm-hmm.
universe is a computation is like saying that the universe is a thought in the mind of God, right?
Right.
It is so general that it's not even falsifiable. Okay,
Mm-hmm.
so I think the but having said that, the what absolutely is true is that the intersection of physics and computer science has been incredibly intellectually fruitful over the last half
Mm-hmm.
century, right? And as soon as you start asking, more specific questions about, well, if we choose to think about the universe computationally, then,
Mm-hmm.
what kind of computer is it? Like,
I see.
how many bits can it store? How many operations can it do per second? Right? What is the
Mm-hmm.
class of problems that the universe can solve efficiently? Right?
Right.
Does it satisfy the Church Turing thesis or not? Okay, though every one of those turned out to be an enormously fruitful question, right?
Mm-hmm.
And
Mm-hmm.
some of the deepest things that we think we know about the laws of physics come from the sort of Bekenstein-Hawking arguments about black hole
Mm-hmm.
entropy. Originating in the 1970s, that basically put fundamental limits on how many bits of information could ever be stored in a bounded region of space, right? And they basically
Mm-hmm.
say, you can store at most about 10 to the 69 power bits or qubits per square
Right.
meter of surface area, right? In
Mm-hmm.
in some boundary enclosing a region. And how do we know that? Well, it's because if you try to store more information than that, you would put so much energy into that region that you would
Mm-hmm.
exceed this Schwarzschild limit, meaning that the region would collapse to a black hole, right?
I see.
Likewise, there seems to be a fundamental limit that you can do at most about 10 to the 43 power operations per
Mm-hmm.
second. One operation per Planck time. Again,
Mm-hmm.
if you try to do more computational operations than that, have a computer that ran at more than 10 to the 43 hertz, then it would
Mm-hmm.
use so much energy that it would collapse to a black hole, right? So
I see.
this Planck scale of 10 to the minus 43 seconds, 10 to the minus 33 centimeters, seems
Mm-hmm.
like a sort of fundamental bound on how finely space and time themselves can be divided. And if you didn't
Mm-hmm.
know better, you would say it was almost like you've identified pixels of space and time, right? Or you've
Right.
identified some underlying discrete structure. Now it can't be quite that simple, because the universe cannot be just like a grid of pixels, because that
Yeah.
wouldn't satisfy the symmetries that the laws of physics
Mm-hmm.
have to satisfy, like
Mm-hmm.
rotational symmetry, or the
Mm-hmm.
Lorentz symmetry of special relativity. Okay, the one thing that, like, everyone studying quantum gravity seems to agree about, right,
Mm-hmm.
is that yes, this Bekenstein limit has to be respected. So there is only a finite number of bits, and not an infinite number
Mm-hmm.
that can be stored in any bounded region of space. And now you can even
Mm-hmm.
combine that with the great discovery of 1998, that the universe has this dark energy, right? Has this
Right.
force that is pushing the galaxies apart on a large enough
Mhm.
scale. If the dark energy is really a cosmological constant, then we seem limited forever to a radius of maybe 20 billion or so light years, right?
Mhm.
For our observable universe, just because anything further away than that is receding from us, so
Mhm.
quickly that the signal from it can never reach us. Okay, and so now
Yeah.
if you take this Bekenstein bound and you apply it to the whole observable universe, then you get a
Mhm.
bound of about a 10 to the 122 power, okay, on the
Mhm.
number of bits or qubits that could ever be involved in any computation or any experiment that we could do within this universe. Now, again, you could, is that a bound on the universe itself? Does that say that, whatever aliens or gods are simulating us, have
Mhm.
only 10 to the 122 bits? Well, not necessarily. After all, we're just talking about the part of the universe that we can observe, right?
Exactly.
And maybe that's very far from the whole of it. Okay, but
Mhm.
at least we now say something, right? We make this remarkable quantitative statement that sort of brings
Mhm.
together physics and computer science, right? And that's a thing that that we've only been able to do since 1998. Okay,
Mhm.
and and then you can further ask, like, what are the if the universe is a computer, what kind of computer is it? Okay, and
Yeah.
so what we learn, some people have tried to use quantum mechanics to say, well, the universe can't be a computer because
Mhm.
the computer would have to be exponentially slow. Okay, now that's kind of a silly argument, right? Because first of all, who's to say that the computer that is simulating our universe, is supposing that there were one, is not itself
Mhm.
a quantum computer? Okay,
I see.
or something even more powerful than a quantum computer, right? Who's to say what the
Mhm.
laws of physics are in some, of some other universe? Okay, but
Right.
secondly, even if it were an ordinary classical computer, it could, maybe that computer would take trillions of years in its time to simulate a
Mhm.
single second, of the time that we perceive, right?
I see.
Who is to say otherwise? Okay, but at least the discovery of quantum computation at least lets us say something, which is that
Mhm.
if the universe is, if you want to think of it as being simulated on a classical computer, right, and if
Mhm.
quantum mechanics is universally valid, then it looks like
Mhm.
the simulation of our universe would then have to suffer an exponential slowdown
I
compared to
see.
the universe itself. So I think it is remarkable that we can, even with all of the qualifiers and the caveats, that we can make statements like that sort of bring
Mhm.
together physics and computer science in that way.
Right. And what would you say? What does the term computationally hard tell us about the limits of the human knowledge and the structure of reality itself? That some problems are hard to solve, even in principle.
Hmm. Well, I mean, okay, so a problem being hard, is always relative to whatever resources,
Hmm.
we might use to solve that problem, right? Uh,
Hmm.
but so famously, the problem of factoring huge numbers, as far as we
Yeah.
can tell, is hard for classical computers, is hard for all the
Hmm.
computers that we have today, but would not be hard for a quantum computer, right?
Right.
So the laws of physics have something to say about this question. Okay, but
Hmm.
the laws of what is computable and what is not computable, right? In principle, those could also be overturned empirically, right? But in
Hmm.
practice, the ones that Alan Turing, and his friends suggested in the 1930s have stood to this day, right? And so if something is uncomputable in the Turing sense, then it
Hmm.
might well just be there might just be no general algorithm to solve that problem consistent with the laws of physics of this universe. right? And that applies to, for example, the halting problem, determining whether a given program will ever halt, or solving a Diophantine equation. So I
Mm-hmm.
give you like an equation, like as in Fermat's last theorem. I ask, does this equation have an integer solution? Or I give you a
Mm-hmm.
set of tiles and I ask you, can these tiles fill the whole plane? Can they tile the plane? Right? These are
Right.
examples of uncomputable problems. And
Mm-hmm.
uncomputable means that there is no algorithm, there's no computer program that will solve any given instance of this problem
Mm-hmm.
correctly, right? And it is remarkable that we're able to make such a statement, right? Ultimately,
Mm-hmm.
because of self-referential arguments that trace back to Gödel's theorem, and
Yeah.
even earlier than that, to the paradox of the liar, right?
Mm-hmm.
In ancient Greece, okay, but where basically you say that if you had a program to solve these sorts of problems, then you could turn that program on itself. Okay, you could get it
Mm-hmm.
to predict its own behavior and then do the opposite of whatever it does. And since that's an
I see.
absurdity, we conclude that the program can't have existed. Okay, but now
Mm-hmm.
a very a common confusion is to say, is to confuse the non-existence of an algorithm with sort of
Mm-hmm.
or being forever ignorant about specific statements, right?
I
So
see.
even though the halting problem is uncomputable for any given computer, that doesn't tell us that for any given computer program, for any
Mm-hmm.
fixed program, that we can't figure out whether that program will halt or not,
Mm-hmm.
right?
And
Clearly there are many programs where we do know if they halt or not.
mm-hmm.
I mean, you can often just stare at a program and say, oh, there's an infinite loop. This one will run forever, right? But very, very often when mathematicians prove a non-trivial theorem, you can interpret
Mm-hmm.
that as saying that some particular computer program will run forever. So, for example,
Mm-hmm.
when Andrew Wiles proved Fermat's last theorem, 30 years
Yeah.
ago, right? You could interpret that as saying that if you program your computer to look for a counterexample to Fermat's last
Mm-hmm.
theorem, to just systematically try all the triples of numbers, and it halt when it finds a counterexample, that
Mm-hmm.
program will run forever. Okay,
I
so
see.
um, so often, with enough ingenuity, yes, for particular instances of the halting problem, we
Mm-hmm.
can solve them, right? And now Gödel's theorem tells us that there will be specific statements that within any given system of axioms that will not be answered,
Mm-hmm.
that will not be either provable or disprovable within that axiom system. Okay, but even then, those statements might be provable or disprovable in a larger axiom system, right?
Mm-hmm.
And then that larger axiom system will itself have unprovable statements, and so on
Mm-hmm.
forever. Okay, but
Right.
there's no limit to needing to add new axioms. Okay, but there's
Mm-hmm.
also no statement of arithmetic that we can clearly say like this is absolutely unknowable. Okay,
I see.
so that's the kind of weird position that we've been in ever since Gödel. And people can argue about what does it mean philosophically, but
Mm-hmm.
at least we can be clear about that much.
Does the randomness of quantum phenomena suggest that there are limits of how much of the universe we can compute or predict?
So I think there clearly are limits to how much we can predict,
Mm-hmm.
right? And you might say, even if quantum mechanics hadn't been true, right, there
Mm-hmm.
still may have been such limits, just
Yeah.
coming from chaos, from
Yeah.
sensitive dependence on initial conditions, right? The fact that
Mm-hmm.
we can never really measure the positions or the velocities of particles to infinite
Mm-hmm.
precision, and if there's even the smallest error in our knowledge of the
Mm-hmm.
current state of a classical physical system,
Mhm.
then chaos tells us that that uncertainty can grow exponentially over time, right?
Right.
It can get amplified over time. I mean, this is the famous butterfly effect, right? Where
Mhm.
if you don't know the position of even a single butterfly, then maybe you also won't know whether there will be a hurricane, who will win the next presidential election, whether there will be war or peace, right, or all kinds of things like
Yeah.
that are downstream of it. Okay, which is also why in all of the time travel stories, like
Mhm.
people who go back in time, they say, well, be careful not to change anything, right?
Yeah.
Be careful to leave every rock where it is, because otherwise you could change history, right?
Mhm.
This is silly. The truth of the matter is that just by being there, just by disturbing the air molecules, they've already changed history, right?
Mhm.
So so this is even in classical physics. But
Mhm.
if the universe had been classical, then we at least could have said, well, there is some definite state of all the particles where if you knew
Mhm.
it, or if a god or a Laplacian demon had loaded it into a computer, then in principle, that demon could
Mhm.
have known the entire future, as well as the entire past. Okay, but
I see.
now, what quantum mechanics says is, well, okay, you could still imagine such a demon, existing outside of the universe, that would know the
Mhm.
whole quantum state of the universe, and
Mhm.
that being could then run the Schrodinger equation backwards and
Yeah.
forwards and over. Even then, that being would only be able to predict probabilities, right?
Mhm.
Not certainties, right? So quantum mechanics is the only place where probability is sort of built into the fundamental laws of physics as we
Mhm.
currently understand them, right?
I see.
Specifically the Born rule, right, which is the rule for how do the amplitudes of different states turn into probabilities of measurement outcomes, right?
Mhm.
It's the only known fundamental law of physics that mentions probability. And there have been many attempts over the years, especially by the
Mhm.
many worlders, to derive the Born rule from the
Mhm.
deterministic part of quantum mechanics. I'm not sure that any of those attempts really succeed without smuggling in the conclusion, right? So
Right.
I think so it seems like quantum mechanics really does tell us that probability is a fundamental phenomenon of the universe, or at least our the
Mhm.
universe as experienced by us. And and things like the Bell inequality really put an exclamation point on that conclusion by
Mhm.
ruling out any local hidden variable explanation for
Right.
what for anything that could be underneath quantum mechanics, right? So we know that if there were some sort of secret determinism, underneath
Mhm.
quantum mechanics, as Einstein hoped for, as many
Mhm.
others have hoped for over the years, then it would also rely on faster than light communication to sort
I
of
see.
coordinate the outcomes of measurements on entangled particles. So now we get that, okay, even the Laplacian demon could presumably only predict probabilities, but maybe you
Mhm.
say that's okay. I can live with that, right? And maybe modern forecasters, Nate Silver, for example, have gotten us used
Mhm.
to, the fact that the best predictors of the future really do think in probabilities. They don't just
Yeah.
think deterministically. They give a range of possible outcomes. Okay, but then there's a further question of, can you even get um, the probabilities right?
Mhm.
And and quantum mechanics puts a limit on that as well. Okay, because in order to even know the probabilities, you would have to know the current quantum state of the whole universe, right?
Yeah.
Which again, presumably, God can know that. A demon outside the universe can know that, but we inside the universe cannot know the complete quantum
Mhm.
state,
Yeah.
because making measurements disturbs the state. It changes it, right?
Mhm.
One of the fundamental principles in quantum mechanics is called the no cloning theorem, right? It says that
Mhm.
you cannot make a perfect copy of an unknown quantum state. In order to do that, you would have you can measure the state, but measurement will not only fail to make a copy, it could even destroy the copy that you have, right?
Mm-hmm.
So, if you combine, well, we can't know the current quantum state of the universe with any certainty,
Mm-hmm.
right? And
Right.
chaos, anything that we don't know about the state, could sort of blow up, could get amplified chaotically over time. Then you
Mm-hmm.
get a, I would say a very strong kind of unpredictability that maybe,
Mm-hmm.
we can't even calculate the probabilities of all future events in a well calibrated way. Like, we as creatures within the universe, subject to its
Mm-hmm.
laws of physics.
Right. And when we talk about randomness,
Mhm.
do you think that the future of linear algebra is random, given the growing area of randomized linear algebra?
Well, I mean, look, linear algebra is a branch of math, and
Mm-hmm.
math does have a sort of eternal quality to it, right? So, all the theorems that Grassmann or whoever proved about linear algebra in the 19th century remain
Yeah.
perfectly valid today, right?
Mm-hmm.
And, you can still teach, from the same books, right? I mean,
Mm-hmm.
what is true is that I think quantum mechanics is sort of maybe one of the most dramatic applications of linear algebra, right? It is the
Right.
demonstration that the whole universe runs on linear algebra, right?
Mm-hmm.
Like linear algebra plus probability, right?
Yeah.
When I took linear algebra as an undergraduate, I could do
Mm-hmm.
it. I could, but I didn't understand like why are we studying eigenvectors among all the possible things we
Mm-hmm.
could study, or singular value decomposition, or these particular or rank, or all these particular concepts. Once you learn quantum mechanics, every one of these concepts has a clear physical meaning, right? And
Mm-hmm.
oh, this is what is being talked about, right? And I see that every time I teach quantum information to undergrads, that
Yeah.
among all the other things it is, all the mind expanding things that it is, it's also like this wonderful way to get a better intuition for linear algebra, right?
Mm-hmm.
And where you see linear algebra plus probability really
Yeah.
syncing together, right? And like why do we use unitary matrices? Because these are the
Mm-hmm.
matrices that conserve probability, that
I see.
that will keep it so that the probabilities will always add up to one. Now,
Mm-hmm.
there are randomized algorithms in linear algebra, that are important, but there are also deterministic algorithms that are important.
Yeah.
You know, in
I see.
computer science, we study all of it. So,
Mm-hmm.
yeah.
Right. And the final question. So, what does the concept of information mean in philosophical sense, especially in quantum mechanics? So, does the quantum mechanics
Mhm.
suggest a more fundamental understanding of what information basically is?
Yeah, well, I mean, for me, like when people say, "Oh, we've learned that physics is really about information," or things like that. Well,
Hmm.
it's again, it's kind of like when we talked about, like, is the universe a computer? And you ask, like, what would the universe have to do in order to not be a computer, right?
Right.
And you could say, like what would physics have to do in order to not be about information? Right?
Hmm.
Because information is really just anytime we have a system that can be in multiple states, and we don't
Hmm.
know which state it's in, and then we learn which state it's in, that is information, right?
Yeah.
And so that seems somehow inherent to the very project of, to the whole enterprise of physics. uh
Hmm.
and so you can say, bits are just a measure of surprise, right? They're just a
Right.
measure of how much you don't know about a system, or how much you could find out about it. And so, if there are n possible configurations that a system could be in, then we say that that
Hmm.
is log of n bits of information, right?
I see.
And so, and of course, the physicists stumbled on this concept even before the computer revolution. They stumbled on it
Hmm.
in the form of entropy, right? Of
Yeah.
thermodynamics, right? That, well, once they realized that they needed entropy to understand about steam engines and so forth and so forth. And then Boltzmann figured out that entropy is really just a measure of information. It's a measure of
Mhm.
how many bits would you need to describe what all of these particles are doing. Uh,
I see.
so 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 that was an extremely important insight, right?
Mhm.
But I would say like it would have been an important insight almost regardless of what the laws of physics had been, right?
Mhm.
And now, of
I see.
course, when quantum mechanics comes along, it changes, some of the rules of information, because it says we can now talk about this more general kind of information, quantum
Mhm.
information, which is measured in qubits rather than in bits. Okay, but and of course that does change some things in extremely interesting ways. But again, you could say, once we make a measurement, then in the end, we are seeing, we are converting quantum information into classical information, at that
Mhm.
point.
Uh,
And there are some number of outcomes, and when we see something, we reduce our uncertainty. We
mhm.
do a Bayesian update or whatever, and this is what we mean by information. It's very hard for me to imagine, any universe except, maybe like a universe with zero information would be, I don't know,
Mhm.
some sort of Buddhist, nothingness, or some,
I see.
or like that you just have some oneness of God. But as soon as you
Mhm.
have any kind of differentiation, you have counterfactuals, you have, different ways that a system could possibly be,
Right.
and then you find out which way it is. Then we're talking about information.
Mhm. Wonderful. Professor Aaronson, thank you so much for this
Of
wonderful
course.
discussion. And I would also like to thank you for your time. And it was
Absolutely.
really an amazing conversation.
Oh, thanks. All right. Well, it's a pleasure.